Hello everyone, welcome back. So, we are in week 5 and this is our first lecture. In this week, we are going to learn how to model strains in 3D, right. So, 3D strain analysis. Okay. So, if you recall, we earlier considered a differential area and then we did the stress analysis for this particular area. Let this dimension be delta x, and obviously, if we apply force along the horizontal direction, then the body is going to deform because this is a elastic body and we have elongation of say along x. So, it is delta of u x, right. Then we can define the strain say epsilon x x is nothing but the change in length along x, in this case it is delta of u x divided by delta x, that is the original length, right. So, that is the definition of axial strain. Similarly, if we consider the same area, but this time if it elongates along say y direction over the initial length of say delta y, and the change in length is delta u of y. Again, we can write down the strain along this direction as per definition is delta u y divided by delta x, sorry delta y. Now, these two are axial strain because the elastic body deforms along x or y axis. Now, let us consider a different situation. If we have the same body, but this time it deforms in a slightly different way. So, the deformed shape, let me draw first, is something like this. Right. So, we have the dimensions delta x, along the vertical direction we have delta y, then there is angular deformation here say theta 1 and here say theta 2, and along this direction the deformation is say delta u x, and along this direction we have a deformation say delta u y, right. So, now we can express say tan of theta 1 is equal to what? We can write delta of u y divided by delta of x. Similarly, in this direction also it deforms by an amount of delta u y, and then tan theta 2 is what? Delta u of x divided by delta y. Then, using these two, we can define the shear strain is equal to theta 1 plus theta 2, and for a small theta, obviously tan theta equal to theta. So, we have delta u y divided by delta x plus delta ux divided by delta y. So, we have the shear strain from this deformed shape, right. Okay. Now, we have defined axial strain and shear strain, right. And again, in case of stress, if you recall, we use sigma for axial stress and then tau for shear stress. Here we have epsilon xx and then gamma xy. The first one is for axial strain and then the second one is for shear strain. Okay. Now, let us consider a body in 3 dimension and see how we can extend this logic in 3 dimension. Okay. Okay. So, we have 3 Cartesian coordinates and then say x, y and z, and then we have a body, say this one, and of course, it is exposed to some external loading and because of that it deforms, right. So, now the deformed position of this body is something like this. So, initially if we consider a line, say here we have P Q, then obviously this point shifts somewhere here and this point shifts somewhere here. So, we have a new orientation which is P prime Q prime. Okay. Now, we can write down the coordinates. So, P has x, y, z and then Q is x plus delta x, y plus delta y and z plus delta z, right. Then point P goes to P prime and then the new coordinate for this point is x plus ux, y plus uy and or let me write it here y plus uy and z plus uz, right. Similarly, Q prime will go to a new location and that is x plus delta x plus ux plus delta ux, right. The next coordinate will be y plus delta y plus uy plus delta uy. Similarly, the last one is z plus delta z plus uz plus delta uz. Okay. Now, what is delta of ux? That is ux differentiated with respect to x times over a length of delta x plus ux differentiated with respect to y times delta y plus ux differentiated with respect to z times delta z. And carefully note all these components ux, uy, uz, they are function of x, y, z, and that is the reason we have their partial derivative with respect to x, y, z. Similarly, we can also write down uy and uz, right. let us just complete the exercise. So, we have partial differential of u y with respect to x times delta x plus u y differentiated with respect to y times delta y plus u y differentiated with respect to z times delta z. And the last one, u z differentiated with respect to x times delta x plus u z differentiated with respect to y times delta y plus u z differentiated with respect to z times delta z. Okay. So, now we can find out the length of the line PQ and P prime Q prime. The reason is, then we can quantify the strain developed over this length PQ, and that is precisely what we are going to do. So, if we have the coordinates of P and Q, then what is the length delta say PQ. So, this is say delta S and then this is delta S prime. So, this we can easily quantify. So, this is nothing but delta x square plus delta y square plus delta z square, right. Similarly, delta S prime square is equal to, we have delta x plus delta u x whole square plus delta y plus delta u y whole square plus delta z plus delta u z whole square, right. So, this we can further simplify. So, this is delta x prime plus delta y prime square plus delta z prime square. So, if we can quantify this delta x prime, so what we have delta x plus delta u of x. So, if we put this expression of delta u of x, we get 1 plus u x differentiated with respect to x times delta x plus u x differentiated with respect to y delta y, then the last term u x differentiated with respect to z times delta z. And similarly, we can also write down all three quantities, right. So, this will be delta y plus delta u y, then delta z plus delta u z. Okay. So, let us just complete the exercise. So, we have here delta u y differentiated with respect to x, delta x plus 1 plus u y differentiated with respect to y times delta y plus u y differentiated with respect to z times delta z. And the last one is u z differentiated with respect to x times delta x plus u z differentiated with respect to y times delta y plus 1 plus u z differentiated with respect to z times delta z. Okay. So, we have all this incremental increase along x, y and z. Okay. So, what we will do next is just see the line, we have PQ and P prime Q prime. Okay. So, now let us figure out what is PQ P prime Q prime square minus PQ square. I will explain that in a minute. Let us first derive the expression and then we will see how we can quantify the strain for this line of length PQ, right. That is the deformed shape. So, we have here delta S prime square minus delta S square. Okay. So, for that we have the expression, we can write delta x prime square plus delta y prime square plus delta z prime square minus, then we have delta x square plus delta y square plus delta z square. Now, for strain obviously we have all these deformations, they are function of x, y, z, and that is the reason we have all these big expressions, but let us do one by one and we will see how we can quantify the different components of strain from this two lines PQ and P prime Q prime, right. Okay. So, for that let us take the first quantity. So, what we have here delta x prime square minus delta x square. Okay. So, let us do that. So, we can express this delta x prime, we know the expression. So, that is delta x plus delta u x whole square minus delta x square, right. So, if we simplify this, delta x square will get cancelled. So, first term is twice delta x delta u x plus we have delta u x whole square, right. Now, if we put the expression of this delta u x that we have already derived here, okay. So, what we will do next is let us put the expression. We have so, this is z actually. So, times delta z whole square plus we have 2 times delta x and then again we have this expression. So, right. Now, if we open the bracket, then obviously we will get all the terms. So, the first one is square of this first term, then square of the second term, then square of the third term in this first bracketed term in the previous line, plus we have twice then delta x delta y times the next term will be delta x delta z times and then the last term is again 2 times delta y delta z, and then we have right, and then the remaining terms will be there. So, we have twice delta x square plus twice delta x delta y. We have first term is okay, then second term is twice delta x delta y. So, this will be y plus the last term is twice delta x delta z, and then we have okay. Now, we can also similarly work out for delta y prime square minus delta y square, right. And then similarly, we can also complete the exercise for delta z prime square minus delta z square. Okay. What we have to do? We have to combine all of them together here. Now, what I will do? I will give you the final expression, and that you can cross verify. So, I leave this as a home task for you, and then the final expression what you get is delta s prime square minus delta s square is twice we have within bracket we have e of x x delta x square plus e of y y delta y square plus e of z z delta z square plus e of x y. I will give you the detailed expression of these terms. So, times delta x delta y plus e of y z delta y delta z plus the last term e of z x delta z delta x, right. So, what is e of x x? This is differential u x with respect to x plus we have half, then u x differentiated with respect to x whole square plus u y differentiated with respect to x whole square plus u z differentiated with respect to x whole square. Similarly, we have capital E of y y, which is u y differentiated with respect to y plus half within bracket u y differentiated with respect to x whole square plus u y differentiated with respect to y whole square plus u z differentiated with respect to z whole square. And the last term E z z, similarly we can write u z plus half within bracket u z differentiated with respect to x whole square plus u z differentiated with respect to y whole square plus u z differentiated with respect to z whole square. So, these are the three axial strain components, and if you look at, we have the linear part as well as the higher order part. So, this up to this is basically linear part, and then beyond that we have quadratic component, right. So, we have our epsilon xx is ux differentiated with respect to x, epsilon yy is uy differentiated with respect to y, and then epsilon zz is uz with respect to z. So, these are axial strain. I am about to explain the shear strain part, which is here, that we will do in a minute, but for the time being what we get, if we know the complete displacement field given by ux, uy, uz, then we can find out all these components. We have linear as well as quadratic term. In this course, we will only consider linear term, so which is here. So, let us complete the exercise. We will consider the remaining 3, and then we will find out what is the strain developed over the length PQ. Okay. So, the remaining 3 E of xy is ux differentiated with respect to y plus uy differentiated with respect to x plus again we have higher order terms. So, we have ux differentiated with respect to x, product the same quantity differentiated with respect to y, then we have uy differentiated with respect to x, and then again with respect to y, product of that, and then last component uz with respect to x, and then okay. Similarly, we can write yz and zx. Here also let me just write the linear part. So, we have u of z differentiated with respect to y plus u of y differentiated with respect to z. Then we have u of x differentiated with respect to z plus u of z differentiated with respect to x. Plus obviously, we have higher order components which I am not writing. You can easily extend and complete that. In our class note, you will get the complete expression. But because in this course, we will only consider the linear variation of strain. So, we will only consider the first part here. Okay. So, now if I just sum it up, what we have here is the displacement fields ux, uy, uz, which are functions of x, y, z, and then if we know the displacement field, then we can actually find out the strain components. We are yet to figure out the strain of the length PQ, that we will do in a minute, but before that let us first identify the displacement gradients first, and then we will move further. Okay. So, we have ux that is differentiated with respect to x, ux differentiated with respect to y, ux differentiated with respect to z, right. Similarly, we have uy differentiated with respect to x, uy differentiated with respect to y, and the last term is uy differentiated with respect to z. And then so this quantity, this matrix, it is called displacement gradient matrix. Okay. So, when we deal with a deformed body, obviously we have ux, uy and uz. Then from this quantity, all of them are function of x, y, z. What we can figure out is the displacement gradient matrix. Okay. Because once we find out this matrix, if you look at the elements, they will actually give us all the strain components. As we progress further, we will see. Okay. So, now what we have derived is p prime q prime square minus p q square. This quantity is nothing but delta s prime square minus delta s square, right. And if you look at the expression, what we have got is 2 times, if I just quickly write it once more, E x x delta x square plus E y y delta y square plus E z z delta z square plus we have the shear components E x y, then delta x delta y plus E y z delta y delta z, and the last term is E z x delta z delta x. Okay. So, what we can do is, if we take this 2 on the left hand side, we have is equal to the third bracketed quantity, right. Okay. Now, the left hand side, if you look at the left hand side, we can simplify. What we do, we have delta s prime square minus delta s square divided by 2 times delta s square. So, we take delta s square in the denominator, which is equal to the third bracketed term, right. Then we can further simplify. So, let me write down the simplified form. So, we have delta s prime minus delta s divided by delta s plus delta s prime minus delta s divided by twice delta s square of this times delta s square is equal to this quantity, third bracketed term. Now, again you can expand this and cross verify whether you get the same term what we have here. Just I leave it as an exercise. So, just take it as a home task, you can cross verify. Now, if you look at this term inside this third bracket, you can easily quantify. We have delta s prime minus delta s divided by delta s. What is this quantity? This is nothing but p prime q prime minus p q and divided by p q, which is nothing but the elongation of the line p q, right. Okay. So, the left hand side, now we have elongation of p q plus half elongation of p q square times delta s square is equal to, again we have that big third bracketed term, right. Obviously, if you have small strain and if you consider linear terms, this quadratic term we can neglect, but if you consider the quadratic term on the right hand side, obviously this term will appear, but for the time being we have, for small strain, we have elongation of p q, right. You can easily see. So, for that let us write down what is the expression. What we will do, we will take that delta s square on the right hand side and we can write E of p q plus half E of p q square is equal to, we have 2 times, sorry, that 2 will not be there, because we have at the first step we have taken this on the left hand side, that is how we derived. Okay. So, we have third bracketed term, but before that we have 1 by delta S square, and then we have this complete term. Now, you can see on the right hand side, if we take this delta S square inside, we have the first term delta x square by delta S square. Similarly, we have all other terms there. So, what are they? Delta x by delta S is nothing but the direction cosine. So, n x is nothing but delta x divided by delta S. Similarly, n y is delta y by delta S, and n z is nothing but delta z divided by delta S. We are almost there. So, what we have here is E of p q plus half E of p q square is equal to, we have E of x x n x square plus E of y y n y square plus E of z z n z square plus we have E of x y n x n y plus E of y z n y n z plus E of z x is equal to n z n x. Now, if we consider the linear term only, so we have elongation of p q, and on the right hand side we will have epsilon x x n x square plus and you can see a similar expression we derived for stress field also. So, the strain components here is these are the 3 axial strains, and then we have shear strain. Okay. So, we have the strain along p q, and we also have identified the strain field given by the axial and shear strain components, right. And if you look at the expression of gamma x y, say this one, obviously it will be equal to gamma y x, right. Okay. So, now we have that complete 3D strain field, and here just notice that we have considered the linear variation in strain. However, I have already shown you the quadratic variation also. So, we start with the displacement field u x, u y, u z, and then first we find out the displacement gradient matrix, and all the components of displacement gradient matrix actually gives us this 3D strain field. Okay. And here of again the diagonal term gives us the axial strain, and then off diagonal terms are the shear strains, right. So, what we will do next? We will quantify at the end of this line. So, we started from this point, which actually goes to this p prime. So, we have quantified n x, n y, n z. Then for this point at the q prime point, we will have n x prime, n y prime and n z prime, that we will first quantify, and then we will move further in our strain analysis. So, with that, let us close here, go through this derivation and just check all the terms, and then what we will do next is we will further continue our strain analysis, and we will see how from this strain field we can find out principal strains and maximum shear strains the same way we did for stress analysis. So, with that, let us close here. We will continue in the next class. Thank you.